And so that comes out to, let's see, 4 squared divided by 5 and divided by 9.8. I come up with 0.33 rounded meters, and that is a foot. And of course now we can see definitely that this is a toy racetrack. So 0.33 meters is the radius. That means the total height is 66 centimeters or 2 feet. And then if we're curious what is actually the velocity at the top, we just use that number and we plug it back in for VF. And here I come up with, let's see, VF squared right there. So square root of GR. And that therefore is, they don't ask for this, but I'll write it down anyway. Maybe because they don't ask for it, I'll erase the underline. And therefore that one is going to be the square root of 9.8 times 0.33. And that comes out to a rounded 1.80 or 1.8 meters per second squared. Looks like we have two significant figures here. Okay, so that means that the car here has a speed of 4.0 meters, and when it's up here it has a speed of 1.8 meters per second. I'm sorry, 4.0 meters per second, 1.8 meters per second. Again, it cannot have 0 there because then it would just fall down because it doesn't go forward anymore. So it has to have some speed, and that speed just matches the centripetal acceleration that matches the weight with which it's being pulled down. But of course the car goes still forward. Another thing here is that if you had a racetrack, a toy racetrack, where you determine what the average velocity is, and then you could say, okay, in order to figure out what the average velocity is, I could say, well, this is how much I need here on the top to get through. It actually means that with the average velocity, you actually have to speed up before you get to the loop here, because you have to have some velocity left. I did this here for a racetrack that I have, where I came up with 2.2 meters per second, but that wouldn't leave me any speed at the top, so I calculated that my average speed of 2.2 actually has to accelerate to 3.3 in order to have sufficient velocity to make it through here, otherwise it falls out. I did that experiment, and I believe I have posted some videos somewhere too. This I call problem H, the golf ball, and I guess I have to, whoops, I have to actually push this back down in here. Okay, so the golf ball, and the problem says as follows. A 47.0 gram golf ball is driven from the tee with initial speed of 52.0 meters per second and rises to a height of 24.6 meters. A. Neglect errors and determine the kinetic energy of the ball at its highest point. B. What is its speed when it is 8.0 meters below its highest point? So in this case here they actually give us the mass, so apparently we will have to use it. So here's first a drawing. So here's the golf ball, and then it's being shot like this here, and then it should follow a parabola, and then we have to figure out what the kinetic energy is up here, and then it falls 8 meters below that, and then we have to figure out, I believe, the velocity over here. So let's see what's given here. The mass is given as 40.7 kilograms. That was supposed to be a 4. Sometimes that kind of smears over there. And the initial speed is 52 meters per second, so V0 equals 52 meters per second. And that actually reminds me to check in the book if we actually use VO or VI. We use, oh good, original. So 52.0 meters per second, and if that just showed up, sorry about that, I was filing or putting on YouTube the other video, the last one. So anyway, I'm supposed to figure out what the kinetic energy is up here, and to a height of 24.6 meters. So I know that h is 24.6 meters, and then there's a b part that says, okay, here there's a height difference of 8.0 meters as it comes down. So it's a two-part problem. Okay, so as it's being teed off at the bottom, it has only kinetic energy, so Ke0, and then at the top it has potential energy and kinetic energy, plus potential energy at the top. And in part A, this is part A actually, in part A we're supposed to figure out what this kinetic energy is, and because they say so, figure out what that kinetic energy is. I'm not going to write that part as 1/2 mv squared, because we're supposed to figure out the whole thing, the kinetic energy. So I'm going to say that kinetic energy at the bottom minus the potential energy at the top equals that kinetic energy. And so this one is going to be 1/2 mvo squared minus mass times gravity times height equals the kinetic energy at the top. And when I plug in numbers, I come up with 1/2 times 0.047 kilograms, because I have to have it in standard units, times 52 squared minus 0.047 kilograms times 9.8 meters per second squared times the height of 24.6 meters, and I come up with that the golf ball has an energy of 52.2 joules. And it looks like we have three significant figures, so 52.2 joules. Then part B, maybe for a change I will actually change the colors. For some reason I like blue and orange. So in part B I have to figure out what is it 8 meters below the peak. So what I have to figure out there 8 meters below is that I have a certain kinetic energy from which I have to figure out what the velocity is. So now at the very top I have the kinetic energy that I just calculated, so that KEF, and then on the right hand side I have kinetic energy, so KE, and yeah, what do I call it now in my part? So this is final kinetic energy part B, and then I consider myself here a new zero level, convenient zero level for the potential energy, and that means that prior to descending to this point here it had actually some potential energy there, so I'm going to add potential energy to that. And I don't know if I want to call this PF here. Okay, anyway, I'm going to plug in the numbers here, so I have 52.2 joules, and then the energy that it has here, which is mass times gravity times height, so 0.047 kilograms times 9.8 meters per second squared times a height of 8 meters, and I come up with 3.7 joules, and that equals 1/2 mass times velocity at point B squared. And then I'm going to do this in one big swap here because I'm kind of running out of time to post this properly on YouTube. So VB equals the 55.9 joules, and then multiply by 2, divide by 0.047 kilograms, and take the square root, and that is then 48.8 meters per second.